Good morning and welcome to this meeting of ISSNAF for the Young Scientist Awards. One of the main activities of ISSNAF is the support of young Italian scientists working for a short or long time in North America. And this recognition of what they are doing in the research field and their contribution to the scientific community of North America is, we believe, an important part of our activity. Today, we are talking of one of the awards given yearly. This is the Bruno Touschek Award. This award is sponsored by the Istituto Nazionale di Fisica Nucleare, the Italian National Institute of Nuclear Physics, an institute which goes back to the history to the end of the Second World War, and covers a wide field of research from elementary particle physics to nuclear physics, and now also to gravitational science, gravitational physics, and cosmology. And all these activities are well represented in Italy and well supported through this institute. And the name Bruno Touschek goes back again to the years after the war, when Bruno Touschek, who was an Austrian physicist, moved to Rome, where he remained for essentially the rest of his life. And Bruno Touschek in 1960 gave a seminar in Rome proposing to build an electron-positron collider. This was something totally new. People had been working on building electron-electron collider to study electrodynamics, essentially, but having electron and positron particle and other particle open new channels for the study of elementary particle physics, as was shown very clearly by Bruno. Bruno had also a background in accelerator. During the war. He had been working on the construction of a Betatron with Wiederoe. So he was a very good theoretical physics, very well knowledgeable in elementary particle physics, but he also had this important background in accelerators. The proposal was accepted with enthusiasm by the Italian scientific community, in particular in Rome and Frascati. And in about 1 year, the first prototype was built. It was called ADA, Anello di Accumulazione, storage ring. And it was followed almost immediately by the project of a larger electron-positron collider, Adone, that was designed for 1.5 GeV and could produce essentially all the known elementary particles, all the elementary particles that were known at that time, through the channel electron-positron, gamma, and then a pair of muon, pion, whatever, up to proton. So this activity started in Frascati, was unique at that time, and raised the interest of the international scientific community. And from the start, ADA, which was a 6-meter circumference ring, magnetic ring, led eventually to the construction at CERN of LEP with a 27-kilometer circumference, and gave many important contributions to our knowledge of elementary particle physics, the standard model, the family of elementary particle, and so on and so forth. So the contribution of Touschek was very important, and was also very important in the design and construction of the storage ring itself. He discovered what is called the Touschek effect. He gave many other contributions. I was lucky enough to work with him at that time, and I have a very good memory of working with him. So for me, it's a very personal story. Okay, having told you all of that, I think we should move on now to the awardees, the finalists of this Bruno Touschek award, Claudio Emma, Marco Siciliano, and Fabio Ravera. Claudio Emma received his PhD at UCLA after studying in London at the King's College and Imperial College. I think in 2017 or 2018. 18. You all received the PhD the same year, I believe, 2018. And he will be the first speaker of this for today. So perhaps, Claudio, you can start your presentation.
Yes, thank you, Claudio, for the introduction. Can you all see my slides, and can you hear me?
Yes.
Yes.
Great. Okay, so yes, thanks again, Claudio. It's really a privilege for me to be able to be here today and to present at this Young Investigator Award Symposium. I'm Claudio Emma, and I'm an associate staff scientist at SLAC National Accelerator Laboratory. And today I wanted to spend a few minutes to present some of the research work that I'm doing right now at SLAC, but also go over some of the work that I did at UCLA while I was getting my PhD. And before kind of diving into the science, I have a very quick slide about myself. Claudio gave a brief introduction, but I thought I would maybe add some pictures to the words. So I'm originally born in Rome. This is a picture of me at 1-year-old, and my family is actually from a small town in Basilicata called Bernalda, which is a beautiful place shown in this aerial shot. If you've never visited Basilicata, I highly recommend it. Since being born in Italy, I've been moving around. As Claudio said, I obtained my bachelor's degree in London in physics with a year abroad, and critically, my exchange year abroad was actually done at UCLA, which turned out to be a sort of pivotal moment for myself personally and also for my career. Because eventually I ended up going back to UCLA to earn a PhD, but this was not before I returned to London for a year to get a master's degree at Imperial College in London, where I studied experimental plasma science. And this is one of the pictures of these kind of plasma instabilities that I was studying during my time at Imperial College. As I said, then I moved on to UCLA, and I was really fortunate enough to be able to study under the mentorship of Professor Claudio Pellegrini, where I got my PhD in high efficiency X-ray free electron lasers. And most of the experimental work there, even though I was at UCLA doing my PhD, was actually done at SLAC. So following the end of my PhD, I actually moved to SLAC permanently, and I've been there for the last 5 years, working at the facility for advanced accelerator experimental tests. And this is, a picture of myself and a colleague actually inside the lab, pointing a flashlight at something, proving that, I actually do work there. And also, myself and some other colleagues in the control room during experimental times, clearly during COVID, as you can see, we're all masked up. So what I want to talk about today is kind of 3 parts of the research thrust that I'm working on. And essentially, these fall under 3 umbrella questions. So it all has to do with accelerators. And my research tries to answer these 3 questions. So the first one being, how can we make particle accelerators more effective at providing the beams that are needed for science applications? And here I'll discuss an example of making high power X-rays efficiently using electron beams. The second question that my research answers is how can we make particle accelerators more accessible? And here I'll talk about some work that I'm doing in shrinking the next generation of particle accelerators 1,000-fold in size. And then finally, I'll say a brief word about how we can improve our understanding of the beams we deliver to scientific users using artificial intelligence and machine learning methods. So the first part is how can we make particle accelerators more effective at providing beams? And specifically, I want to talk about generating high power X-rays with electron bunches. So a brief slide about motivation, why high power X-rays are useful probes and of the natural world, and why accelerators are used to generate them. So I have three sort of highlight examples here that show why X-rays can be really unique probes of microscopic structure, both for biology, material science, and fundamental physics. So starting from the left here, this is an image of the Trypanosoma brucei virus, which is responsible for the African sleeping sickness disease, which affects, tens of thousands of people globally. And you can see that using, X-ray diffraction imaging, you can actually recover the actual shape of the virus and study this in great detail with sub-nanometer resolution. And of course, when you can study these viruses with good resolution, spatially and temporally, you can also come up with, of course, as we know, cures and drugs that try to tackle them. So obviously, the COVID pandemic has taught us that this is very important for society at large. So there are big biological applications for X-ray sources. Quantum materials, of course, are also exciting for example, representing magnetic bits on future disk drives, and this is something that X-ray sources are used to probe at the nanometer level. And of course, high power X-rays can be used to study fundamental physics. For example, at the focus of these very, very high power X-ray beams, you can get nonlinear phenomena like two-photon Compton scattering, which are still yet to be fully understood theoretically. So the through line here is that future experiments, whether it be in biology, material science, or fundamental physics, they want 10 to 100 times more X-ray power than state-of-the-art sources. So we need a way to increase the power of X-ray sources, and this is what I studied during my PhD. So I'm going to try to summarize this in one slide, but the real question is, how do you maximize the X-ray power of existing sources? So first you go to the brightest X-ray source that exists, which is a free electron laser, and you ask, how do we maximize the power of that? And for those of you who are not familiar with free electron lasers, they're essentially depicted schematically in this figure here. They are devices which consist of an electron source, an accelerator, which is typically 1 kilometer long. This generates an electron bunch that then goes through this undulator magnet that makes the electrons wiggle sinusoidally and emit X-rays. If the undulator magnet is tuned correctly, then the electrons will make one sinusoidal oscillation while the X-rays slip ahead by one wavelength. And that enables this coherent interference between each electron with its other microbunch, as they call it, as the beam traverses through the undulator. And this allows for a very intense production of X-rays. It's about 10 billion times brighter than the next brightest source, but really only 0.1% of the beam energy is converted to X-rays. So even though this is the brightest source existing, one might ask, why can't we make more than 0.1% efficient conversion? And the reason is that at a certain point, once the electron bunch loses about 0.1% of its energy, the synchronism that I was just describing, where the electron makes one oscillation and the X-ray pulse slips ahead by one wavelength, is lost because now the electron energy has changed, so it makes a different route through one period of the magnet. And so what you can do is kind of tune the magnetic field as the electron beam loses energy to kind of taper it to the energy loss. And that way you can continue the interaction. And this is something that's been known since the 80s. And the trick is really to make all the electrons lose energy at the same rate for as long as possible. So what was really my contribution in the field? Well, in my PhD work, we took this technique of tapering and we tried to basically create a situation where the electron beam was prepared in such a way that when you taper the undulator magnetic field, you extract as much energy as possible. And now, of course, this very technical diagram here describes the experiment in detail. Essentially, trying to summarize this briefly, what we did is we passed the electron beam next to what's called a dechirper. This is just a corrugated magnetic structure, which imparts this banana-shaped kick on the beam. And then you can essentially use parts of the electron beam in different parts of the undulator to generate a high-power X-ray pulse in the first part, shift it to the head of the beam in the second part, and now you really have a strong seed. And that strong seed, combined with strong tapering, allows you to increase the efficiency, by a significant fraction compared to previous methods. And the two achievements here are, using this kind of method, which we call fresh bunch self-seeding, we were able to achieve world record brightness for an X-ray FEL at the time, increasing the efficiency by about 100% over previous methods. But importantly, what we showed is that this kind of method can be used as a blueprint in future machines that are maybe more flexible, that are specifically designed for high efficiency, to go beyond 100% increase to maybe a factor of 10 or more. So this is one of the things that I contributed to, and also it was coupled with a series of theoretical studies that kind of described why this method was most adequate going forward as an efficiency booster. So now I'd like to switch gears very quickly to the second question, which is how do we make particle accelerators more accessible for the next generation of experiments? And this has to do with shrinking the particle accelerator itself about 1,000-fold in size. So why exactly do we want to shrink particle accelerators? Well, I think that the motivation is summarized kind of well by this one figure here on the left, which shows accelerators being, large, costly, and time-consuming projects. If you look at the cost for various large accelerator facilities in billions of dollars, and the amount of time that it takes to construct these facilities, we're talking about, $1 to $5 billion, depending on the size of the accelerator, and anywhere between, 5 and 10 years to construct them. So it's very difficult to construct many of these machines, and typically they're very oversubscribed. There's a lot more science that can be done, which is not done because there are simply not enough of them. So one of the techniques which has been proposed for several decades now is, why can't we just shrink the size of the accelerator itself? That way you don't have to build a very large tunnel, the construction time goes down, and so does the construction cost. And maybe you could put an accelerator in every university and start doing much more high-risk experiments, which could have certain payoffs that you don't even know exist yet. And so the answer to this is to kind of move away from the technology that's used in these conventional accelerators, which is microwave cavities, to plasmas. And plasmas are interesting because they can support electric fields that are about 1,000 times larger than these conventional accelerators. So that means that with 1,000 times larger field, if you want, say a GeV or a TeV of energy, you can make the accelerator itself 1,000 times smaller. And so this technology is being pursued actively by many research groups, and it's very interesting. But unfortunately, because of the large fields that exist in these structures, the stability of them is actually quite far right now from the requirements for, say, building the next linear collider. And so the question then becomes, this transformative technology exists, how can we actually leverage it for high impact near-term applications? And this is where my contribution comes in. So very recently, actually, just a year ago, myself and a group here at SLAC proposed to use these plasma accelerators to make a new kind of light source, an attosecond X-ray source. And these attosecond X-ray pulses are very interesting because they're the shortest pulses of light that are made in any light source, at all wavelengths, and they can be used to study the quantum motion of electrons in atoms. So quantum chemistry here, there are very large number of applications, and plasma accelerators themselves actually lend themselves to generating very short beams that are extremely bright with this kind of structure here that I'm showing on the left, so that the back of the beam has higher energy than the front. And what I proposed in this paper is to take these plasma accelerated beams and compress them further to very short spikes of nanometer duration. And this way, this new design for an attosecond based light source would not only shrink the size of the accelerator, but do something that conventional accelerators can't do, pushing once again the peak power up by 5 to 10 compared to existing state-of-the-art sources, and with potentially improved stability. So after this proposal last year, we received some funding at the lab to pursue this experimentally, and I'm currently the co-PI on an experiment at SLAC that seeks to demonstrate this in the next couple of years. So stay tuned for those results. And then finally, I just have a few minutes left. So I'd like to talk about the very last part of my research, which is how can we improve our understanding of the beams that we deliver to scientific users. In this case, I want to tackle kind of two practical problems that exist in accelerator science, which involve delivering beams to users and actually measuring the properties of these bunches as you deliver them. So there are two issues that come about when you try to measure beams. Number one, when you measure beams, typically you do this by, let's say, inserting screens in the beam line, and you have to intercept the bunch itself. So you usually can't measure the electron beam properties and simultaneously deliver to experiments at the same time, which is unfortunate because this costs setup time and you can't, do both at once. And also, as beams become more intense in these machines, you start to actually damage the measurement devices themselves. Here you can see broken screens and broken wires, which are typically used as diagnostics inside of accelerator machines. So what is the solution? At least one solution, the proposed solution that I've been working on, is to use artificial intelligence or machine learning to essentially predict beam properties without intercepting the bunch itself. And this kind of complicated schematic here shows one of the accelerator facilities that I work on that's called FACET, which has a number of diagnostics along the beam line that, for example, measure radiation emitted by the bunch non-destructively as it travels through magnets. And what you can do with these kinds of non-destructive diagnostics is you can train a machine learning algorithm to essentially map or find the mapping between these non-destructive readings and what the electron distribution would look like if you were to put a screen in the way. And this is very much similar to what people do with self-driving cars. After the machine learning algorithm has seen enough examples of beam distributions with different machine settings, it can map those settings to the distribution itself. And here, of course, improved understanding of the beams delivered to experiments is the key, but of course also reducing setup time and opening up access to more science is really the most important part of this kind of research thrust. And now I think I'm almost exactly out of time, so I just wanted to quickly recap that I tried to give a quick overview of these three main questions that my research thrusts try to answer. How to improve the efficiency, the access, and the understanding of beams we deliver scientific users. And I hope that this has been, clear enough that that you can see that this affects, broadly the delivery of beams to multiple scientific experiments, whether it's biology, chemistry, or fundamental physics itself. And so with that, I'd like to close. And before I do, I just wanted to say thank you to ISSNAF for giving me the opportunity to present again today. It's a great honor to present next to the other finalists. And I'd like to thank also some of my mentors, a great Italian scientist that I've had the pleasure to work with, including Professor Pellegrini, and currently now other Italian scientists at SLAC, like Professor Ago Marinelli and Dr. Alberto Lutman, that have been very influential in my career so far. Thank you.
Questions?
How do we do this, Claudio? Can I just ask? Or
yes. I think you can.
Okay.
Oh,
so,
sorry,
Claudio,
different Claudio.
Well, sorry, it doesn't matter. Yeah, there's two Claudios. Actually, I have a question about machine learning. First of all, thanks for a very clear and interesting presentation. I'm curious about the machine learning thing at the end. When a driving car has to deal with, I don't know, crazy people trying to cross the street where they're not supposed to, and so on. Your beam, in some sense, seems to me entirely predictable and at least in principle calculable. And so the connection between the signals you get non-destructively and the properties of the beam should be, there should be some sort of a one-to-one correspondence, at least in principle. And so I'm wondering whether the machine learning is something that improves things a little bit, or is essential for some reason that I don't understand, sort of.
Yeah. So no, that's a really good question. Of course, you're right. There is a one-to-one correspondence in, say, the linear dynamics of beams going through an accelerator. We know exactly how the bunch is supposed to propagate, but there are, a series of unknown unknowns that are very much practical. For example, magnet misalignments or RF temperature drifts that cause, the energy to move around during the day. And this is not something that we fundamentally, from a physics point of view, can put inside the models, because, it's kind of, in a sense, random fluctuations that have to do with either diurnal shifts in temperature or things like that. So in this case, the machine learning itself, what it does is it can find the pattern from many, many sensors. You can feed it all of these temperature sensors, all of these, energy sensors, and so on. And basically, it's very good at finding the unknown unknowns, if that makes any sense. Specifically, when it comes to, say, misalignments that you wouldn't expect you would put in your simulation model. Does that sort of?
Okay, that's fine. Yes. Okay.
So can I follow on that one? Because I was also curious about this machine learning application. So in your training set is what? Is it like destructive reads, or because obviously that's usually the problem. If your training set and something changes between your training set and the actual experiment, then you may have some problem. How do you make sure that your training set is in the same identical conditions as your actual experiment?
Yeah, that's a really good question. So the training set is destructive readings that you see here. So many measurements of the electron distribution as we change some parameters deliberately in the machine. For example, the strength of the magnet in these bunch compressors. And then you'll see many different shapes show up here. So that's the training set. Now, the second part of the question is, how do you make sure that the training set doesn't change after you turn your destructive diagnostic off? And this question is, I would say, somewhat left unanswered. So one way to try to minimize this effect is to, let's say, train your machine learning model, the morning that you're going to do your shift, take a small amount of data, and then, say a few hours later, you basically take a little bit more data and make sure that your predictions haven't completely gone, far away from where the machine was in the morning. And this is called, retraining typically. But the question of how often do you have to retrain is still, not answered. It also depends on the complexity of your facility. We have a 1 kilometer accelerator. So obviously, if you have to retrain your model every 5 minutes, that's no good. What we're able to show, nowadays is that, for example, in experiments we did at UCLA, we were able to train a model to predict the beam distribution. And then 5 months later, after the machine had changed, configurations had changed, that model was actually still pretty close to where you're predicting the beam quite well. So then you only have to add a little bit of data in retraining before you get high fidelity back, if that makes sense.
Other questions?
So Claudio, sorry, if you actually go back to your first topic, how hard it is so those are presumably those beams, those X-rays are linearly polarized, that as they come out of your undulator. How hard it is to make them circularly polarized?
You can, it's not so difficult. You just change the geometry of the undulator. So you can make a planar polarized undulator or helical polarized undulator. You can have cross polarized undulator. In fact, this exists. So,
Yeah, I'm not in the field, right? So I'm just, okay.
Yeah.
Right.
Yeah.
Right. Okay. All right. Thank you.
Okay, if there are no other questions, I need to apologize because before I forgot to introduce the jury. The jury is composed of 3 professors. They selected the 3 finalists out of all the applicants to the Touschek Award, and they will select the winner out of the 3 finalists. They are Professor Tommaso Treu from UCLA. He's an astronomer. He's in the Division of Astronomy in the Department of Physics and Astronomy at UCLA. Professor Giorgio Gratta of Stanford, and Professor Pietro Musumeci, again from UCLA. They cover with their experience and their activity all the areas which are being discussed by the 3 finalists. So nuclear physics, elementary particle physics and cosmology and particle accelerators. So thank you, Tommaso, Giorgio, and Pietro for doing this work and for helping ISSNAF with this Young Scientist Award. Okay, having said that, we can move on to the second finalist, Fabio Ravera. Fabio, would you like to start?
Yeah, sharing the slides, going to full screen. Okay, I hope you can see my slides. Okay, so first of all, I would like to thank ISSNAF for this great opportunity to present my work. I am an associate scientist at Fermilab, and today I would like to focus on my presentation on one of my activities, which is the construction of a new auto tracker for CMS. And so, as a particle physicist, I'm mainly interested in replying to the big questions of our field. For example, what is dark matter? What is the nature of gravity and why it's so different from other forces? Why neutrino oscillates, or why there is such a big asymmetry between matter and antimatter in the universe? And there are different approaches to tackle these questions. So the one that I choose in my career is to look for collider physics, where we take two different particles, we make them collide, and we obtain new particles. And by investigating this kind of events, we might shed light on one or maybe more of these questions. So in particular, my experiment is one of the 4 experiments at the Large Hadron Collider. This is a proton-proton collider, is 27 kilometers, is the largest machine built by humankind, and the CMS detector is located over here. The energy in the center of mass is 13.6 TeV, and we have a collision rate of 40 megahertz, so 40 million bunches every second that intersect each other. And our detector look like this. We like to call it the cylindrical onion, because like an onion is made of several layers. Each one of these layers are different detectors that provide information that combined together allow us to reconstruct the particle properties. And it's a quite massive detector. It's 14,000 tons, 50 meters tall, almost 30 meters wide. And for today, I will not be able to go to all the sub-detector, but I would like just to focus on the outer tracker, which is over here, the blue part. And the picture that you see is actually the picture of the current outer tracker that we will replace with as a part of my activity. So the reason why we need to build a completely new detector is because LHC will be upgraded, going through the so-called high luminosity upgrade. So basically in 2026, the machine will be upgraded in order to provide instantaneous luminosity 7 times larger, basically 7 times more collision per second. And we're expected to collect 4 inverse attobar in 10 years, which means that basically in a month, we will be able to collect all the luminosity that we collected in 4 years of run 2, and that in a single day, we will be able to produce 130,000 Higgs boson that we just discovered 10 years ago. So this is quite impressive. Of course, this is come with some drawbacks because the data taking condition will be extremely harsh. In particular, you see in the right, this is what we are going to face with up to 200 protons that are going to collide in the same instant. And it's critical for us to be able to identify all these particles, associate them to the correct vertex, because maybe the physics that we're really interested into is in this vertex over here. So another important point that I need to introduce to discuss why we're building this kind of tracker is the concept of triggers. With 40 million collisions per second, and each event is roughly 1 megabyte, we have a detector that receives 40 terabytes per second. So that, put in perspective, means 10,000 HD movie per second. So it's definitely too many data to be able to save them all. So CMS uses a set of layers of triggers, and in particular the so-called level 1 trigger decides every 12.5 microsecond at 40 megahertz which events are interesting enough to be downloaded from the detector for further processing. To understand why the tracking is fundamental for this aspect, you can look to the plot here. Here you see the trigger rate for a single muon trigger as a function of the threshold of the transfer momentum of the trigger, we usually call it PT. So in red is the rate that you're going to get if you take the current trigger strategy and you bring it to high luminosity data taking conditions. So you basically see that the rate is pretty high. In black instead is the rate that you will get if you also include the track information in reconstructing the muon at the level 1 trigger. And basically what you see is that a change in the threshold, you are able to effectively reduce the rate. This is very important because we don't have just one trigger. We have several triggers that need to work together, but we have also a maximum cap on the rate that we can store. So if we have one trigger that fires way more than others, automatically we create a bottleneck. So how the tracker can provide information at the level 1? Also in this case, we face the same problem of the rest of the detector. We have too many data to send them all. But we can use this concept of called PT modules, which you see in the sketch is made of 2 sensors, closely spaced and read out by the same electronics. And thanks to the high magnetic field of CMS, particles with high PT, high transfer momentum, will arrive almost straight from the interaction point. And the 2 hits on the 2 sensors will be closely spaced. And in this case, we create a so-called stub. For low PT tracking, instead, this will arrive with a curvature. And so the 2 hits will be largely separated and the stub is not created. The main advantage is that just looking at the stubs, we have roughly a factor of 20 data reduction. And so we can take all the stubs, send them continuously to the backend electronics, where we do tracking at 40 megahertz. Then in the detector, we are actually going to have 2 types of PT modules. Closer to the interaction point, where we need a bit more granularity, we are going to use PS modules made of a layer of pixel and a layer of strips. And farther, where granularity is less a constraint, we are going to use a 2S, so made of 2 layers of strips overlapped. This is basically the concept, and now I would like to move to my contribution to the project. And as you can imagine, this is not a design that was easy to be achieved, and we went through quite a long R&D. And in particular, at Fermilab, we did a lot of tests, and in particular, test beams. In fact, we have a very nice test beam facilities with a very nice telescope that allows us to track precisely the position of the particle. And in the middle, we put one of the first prototypes. This is a 2S prototype. You clearly see the strip, at least in the top, and the other one is on the back, not really visible. And we did a full characterization. But the result that I think is the most interesting is the fact that we can prove that we can reconstruct the stubs. This basically hits from high PT tracks. In particular, here you see the stub reconstruction efficiency as a function of the PT. Here we don't really have a magnetic field, but we emulate it by rotating the detector with respect to the beam direction. And so what we observed is a very sharp turn-on curve. That is what we would like to see. And also that by changing the window in which we accept the stub, you can actually change the threshold in PT. So after all the R&D that we completed, basically, now we are moving towards the production phase. So just to give you an idea of the scale of the detector, this is 1/4 of the full tracker. If you look at the dimension, we speak about 120 centimeters of radius and basically 5 meters of length. 0, 0 is in the interaction point of the protons, and whatever you see in blue is the outer track. Then the outer track has, as I was saying, the PS in blue, closer to the interaction point, and the 2S here in red far. So at Fermilab, we plan to assemble and qualify 2,500 modules. In particular, I'm responsible for this part, which is 1/6 of the overall production for CMS. And the time scale is shown at the bottom. In the spring, we're going to start the pre-production that will last 1 year and followed by 2 years of production. So we're really getting ready for assembling the real modules. Assembling this device is quite complicated. We had to go through several steps, so I cannot really go into all the details. But I would like just to point to one very important part of the whole assembly, and it's the fact that the whole stub reconstruction works only if the top and the bottom sensor are perfectly aligned. If you have a small misalignment, you cannot anymore reconstruct the stub. You don't know where, if the two hits were within a center range, center window or not. So at Fermilab, we designed this hypersized fixture that you see on the top. On the left, you see just the bottom sensor with the spacers on the edges. And on the right, you see also when we put the top sensor on top of it. Then, of course...
5 minutes.
Thank you very much. Then, of course, despite the fact that there is a very hypersized fixture, something can always go wrong. And so we needed to do a full metrology of what we call sensor sandwich. So we set up this 3D robot equipped with a laser that scans the edge of the two sensors and is able to reconstruct offset and rotation. And here the specs are quite tight, 400 microradian maximum of rotation. And so skipping all the other steps of the production, at the end, what you get is something like that. On the left, you can recognize the strip sensor. On the right is the strip pixel sensor. And we already assembled around 10 of these devices. And it's not just done to check that we are able to do them, but also the fact that we use those for optimizing the production line. This is just part of the work because, of course, then the module needs to be fully qualified. And therefore, we set up the laboratory for fully qualifying the modules. So we have both single test stands and burn-in test stands. This is actually another of our responsibilities that allow, so this setup allows us to do thermal cycles for several hours in order to see if there is any mechanical or electrical damage on the module. And all of this is critical because we need to identify the modules to be installed into the final detector. And the thing that we have to keep in mind is that the module quality will directly affect the CMS physics performance. We're speaking about thousands of physicists that are waiting for this data. So it's quite important task list. And since we already developed several of these test stands, we also have a leading role in the definition of the quality assurance and quality control. Just another small thing, so what it means actually to test this module. So you need a DRQ system, and this I'm actually responsible for the development for the international CMS of this software, which allow to fully characterize the detector. It's actually, I would like to point is the fact that it actually have a wider scope because this software is meant to be used for the full tracker, both inner and outer tracker, but also for the whole lifetime of the project. So the plan is to use this exact software for the data taking, which is not usually the case for our for this kind of applications. What the software does is that provides you a set of outputs that you can look at and understand the quality of your detector. I would like just to show you one, which is quite emblematic, is the noise as of, for all the channels. And already from this plot, we can understand several properties of our detector. So for example, high noise might indicate presence of scratches on the sensor. A slightly lower noise might indicate problems on the wire bonds that connect the sensor to the electronics, and very low noise can indicate missing connection between the readout chip and the hybrid, electrical hybrid, which they are connected to. Of course, it's easy to see this plot, but imagine once you have thousands of modules assembled all around the world, so this is not really practical, and therefore we are also leading the development for the grading software that analyze these kind of plots and store the information in the production database. So this brings me to the summary. So the goal of this upgrade is to maintain and even boost the physics performance of high luminosity LHC. We're going to use this new concept of PT modules, which allow us to do tracking at 40 megahertz. And at Fermilab, we will build 2,500 modules, going through a quite challenging assembly. As I told you, it's critical to identify the modules that we're going to install into the detector, and our Fermilab group has a leading role in all the aspects of the module production. I would like just to steal 10 more seconds, because of course this is quite extended work, and I couldn't do anything without all the people I'm collaborating to and speak about students, postdocs, technicians, engineers, and scientists. I try to make a collage of all the phases. I would say the pretty happy phases. So a big thanks goes to them, because all this work would not be possible without their contribution. Thanks a lot for your attention.
Questions?
I guess I can ask, I'm kind of the troublemaker always. So Fabio, again, thanks for a very clear presentation. I'm actually, if you go back to your very first slide, or maybe the second one, maybe the first one is just the title, but that will be the second one. You mentioned gravitons, and I'm a little bit fixated with.
Yeah.
I started with particle physics, and then I'm really fixated with gravity. And in fact, Claudio Pellegrini, I think in his early career, studied general relativity, if I remember right, Claudio. So can you? But I'm a little bit puzzled that the LHC. So I'm not sure exactly how. LHC can actually say something about nature of gravity. So maybe you can.
Yeah. So I actually I skipped this part because I decided to focus more on the other part. I'm actually working also on an analysis that search for dihedral, not only dihedral, but to simplify dihedral, resonances decaying to dihedral. And among various theories, there is the idea of KS radion and gravitons to be able to decay into dihedral. So that is one of the examples that we follow, which is kind of a parallel idea with respect to other searches, but it's quite popular. I mean, not really popular, sounds not great, but it's quite a common approach that we follow in both CMS and Atlas, and we actually we hope to present our results on Morion. We don't know still if we found something because it's still blinded, but we will definitely be able to put further constraint on gravitons and radions using dihedral searches.
I see. Okay. And then I have a totally opposite question in terms of, so this is actually very technical. So how many years with full luminosity? Sorry, this is a question about radiation damage.
Yeah.
So how many years do you expect your modules to last at full luminosity?
So we did all our studies for inverse Atterburn. So it is for the innermost layer is 1.5 E15 Newton equivalent per square centimeters. We usually always speak about the fluence. So I wrap up a bit. There are usually two types of damages: ionizing those that mainly affect the chips. The chips should get 100 megarad. We test all the chips at 200 megarad, and the sensor, let's say PS that are a bit closer, are a bit higher. This is 1.5 Newton equivalent per square centimeter. We also test everything at that level. We check that basically the amount of data that is collected after that irradiation is well above the noise that we get also at that level of irradiation. So we are confident that this detector will survive. And to be honest, it's not really that we are confident, we have to be sure, because the outer tracker cannot be replaced without basically stopping the machine for probably a year. These compared to other detectors like the pixel that is built in CMS in order to be able to extract it, the outer tracker is basically connected to the solenoid, so it's not accessible. So that's also another reason why the quality control of this module is so critical, because if something goes wrong, we cannot do anything anymore.
Thank you.
Other questions?
Yeah, I have a technical question too. What are the considerations that goes in the distance, separation between the strips and the material? I mean, what's the physics? There is a physics or there is spatial limitation, constraint limitation?
There is actually physics. So I probably omitted that in my slides, but there is a variation, so we don't build only one thickness in one distance between one spacing between the two sensors, but actually we build 5 different spaces depending on the position of the module in the tracker. The reason is that imagine the particle that has a curvature. This is like a circumference. So if you're closer to the beginning to the interaction point, you're just at the beginning of the circumference. So to look for an angle and distinguish high PT from low PT, you need larger distances. So you have more lever arm basically. If you move farther, instead the particle will arrive already with a larger angle basically because you are far in the curve in the circumference. Then at this point you go to smaller spaces. The range is between 1.6 millimeter and 4 millimeters.
Okay. Other questions? So if not, we can move to the last finalist, Marco Siciliano, who studied in Padua and got his bachelor and PhD in Padua. And Marco?
Okay, you should hear and see me. Can you confirm everything?
Yes.
Yes.
Okay, thank you. So, good morning, everyone. First of all, it's an honor to be here presenting my work. I'm Marco Siciliano from Argonne National Laboratory, and I'm going to speak about nuclear collectivity and the relationship between these and the nuclear structure. So first of all, let's introduce myself. So as was said, I've been studying in Padua, and during my whole career, I have been working on the study of nuclear structure and collectivity. and nuclear shape via combined particle and gamma spectroscopy. And this has led me to work on several laboratories all over Europe and all over North America. And in particular, it led me to work with the most powerful gamma ray spectrometers that exist nowadays. But let's start from the beginning. So let's start from the question, why should we study the nuclear structure and the atomic nucleus? Well, the fact is that even if the atomic nucleus has been known and discovered since more than 100 years, nowadays there is no theory or model that can fully describe the nucleus and the nuclear interaction. There are several reasons because of that, but the main reason are, first of all, that the atomic nucleus is a quantum system. So there are many features that cannot be directly observed, but we have to infer them from by observing other quantities, or we can infer by comparing these quantities with the theoretical models. Then another reason why it's so difficult to arrive to a description of the nuclear interaction is the fact that the atomic nucleus is a many-body system. In fact, for example, if you think about the lead that naturally exists, that counts more than 200 particles. And if we have to consider the interaction of all these particles, so neutrons and protons, with themselves, is going to be very expensive from the computational point of view. But on the other hand, even if there are many body systems, this number of particles are not so large that we can make some assumption or some approximation, like for huge system with the billions of bodies and so on. And then last but not least is the fact that we are, as I wrote here, we are made of stardust. So we need theories that are able to describe the atomic nucleus that exist in us, in our laboratories, but as well that can exist even in galaxy or inside stars. So at this point, it becomes very difficult to describe this system that exists under very different conditions. However, if we, between this model, one of the most explored, the most used one, is the one that is called shell model. The idea behind this model is the fact that we have our nucleons that are protons and neutrons, and we want to store them, and practically we store them inside the orbitals. And as soon as we fulfill such orbitals, our nucleus become more stable, and we reach those that in nuclear physics we call magic numbers. So if we within this framework, practically what we have is that we can kind of describe the nuclear interaction, practically dividing it in two different information. On one side, we can have the information related to the fact that we are storing the neutrons and protons inside these orbitals, while on the other side, what we can have is that we take into account all the correlation between the nucleons that can be quadruple, octuple correlation that drive the nucleus to a more deformed shape. While, for example, we can have the pairing force that is also described in this second part of the nuclear interaction, that while it drives the nucleus to a more spherical shape. And practically what we have is, as soon as we go to study the shape of a nucleus, we can directly investigate this second part of the nuclear interaction. Just to give an idea, what we have is that practically when we are close to a magic number, we are in this kind of stable condition, so our nucleus tend to be more spherical. And as much as we increase the number of nucleons inside our nucleus, we have that we go to a more deformed behavior. And a way to explore, to study this so-called collectivity is to measure that are called transition probability between the excited state. And one of the most valuable information come from what the so-called B2 probabilities. And that is very important also for another reason, because not only give information on the collectivity, but can really give the information about the shape of a nucleus, because we can have that our nucleus in its ground state or excited state can be spherical as a tomato, or can be prolate as a carrot, or oblate as a pumpkin, or can even be something in between, like a kiwi that is triaxial. So if we want to study such a collectivity, in particular, how this collectivity evolve and so have a very deep information on the nuclear interaction, I personally think that the best region to do that is the Z equal 50 region, because here we can find the longest isotopic chain between those that are called doubly magic nuclei, so those nuclei that are magic both for protons and neutrons. And so that means that here we can study not only stable nuclei, that are those that exist in nature, but even very exotic ones where the number of protons or neutrons is very unbalanced. And here are respectively the black ones are the stable in this picture, and the colorful ones are instead those that are radioactive. And here, let's say that this is my field of expertise, because during my career, I have performed several studies in order to address the physics of this region. So let's start focusing on the team case. So as I said, the team, so Z equal 50 is supposed to be a magic number. So as I said before, in principle, we would expect to have dominance from the pairing force. And if we look at observables, like, for example, the excitation energy of the low-lying state, these are suggesting such a behavior. We can see these 2+ state and 4+ state that are rather constant in energy as a function of the mass. And this is a hint of this pairing dominance. However, as soon as we have a look at the transition probability, that is the picture here on the right, we have that we don't find anymore that very beautiful parabolic trend that I show before. In particular, when we go to study the neutron deficient side, so let's say those experimental points on the left side of the picture, absolutely here we don't have at all this parabolic trend. So at this point, during my PhD, we performed an experiment in order to investigate such an exotic nuclei. We performed this experiment in Ganil, and thanks to this very advanced technology and detector that we have there, we have Agatha, that is the cutting edge on gamma ray spectrometers in Europe, and thanks to VAMOS, that is a magnetic spectrometer that allowed the identification of reaction channels, and also thanks to an unconventional use of a multi-nucleon transfer reaction, it was possible to explore and investigate this nuclei. And here in the picture, we can see all the nuclei that were populated during this reaction and the very nice identification that was performed with VAMOS. So during this study, what I got, not only I was able to determine the transition probability for the 2+ state, that are those red dots on the top part of the figure, but also for the very first time, I was able to determine the transition probability from the 4+ state. And this new result, in particular, the very precise one in TIN 108, this very first result was very important for the fact that for the first time we could focus our attention not only to the 2+ state, but we can have a look also to the 4+ state and try to understand what is happening. And then comparing the experimental result with the theoretical models, we could understand if there is really pairing dominance. And actually, not at all. This is not at all. So while the excitation energy suggests this pairing dominance, what we have from the comparison with theoretical model is that the transition probability of the 2+ state practically is not affected at all by the pairing force. So I can change as much as I want the pairing force inside the nuclear interaction and nothing absolutely changes, as we can see from the different colorful curves on the top side of the picture. While for the 4+ state, thanks to this new result, here we have that in order to reproduce the new experimental result, we have to find a very delicate balance between quadrupole and pairing forces. And in fact, thanks to that, we could explore this part of the nuclear interaction.
5 minutes.
Nuclear interaction. Okay. So after that, so let's have a look also at other cases. So another question can be, what happens if we remove 2 protons or several protons from the Z = 50? So is it going to change the structure of this nuclei? Where naively one would expect that these are just 2 protons. For example, the cadmium nuclei are just 2 protons. So one would expect that the structure remain the same. And actually there are theoretical models that try to describe cadmium, tin, tellurium, so all these neighboring nuclei within the same framework. On the other hand, we had that, for example, cadmium nuclei has been always considered a kind of a textbook example for nuclear vibrators. And again, during this study of mine, actually I explored this structure of the cadmium nuclei, and this is actually seems that is not the case again. So what we have is that cadmium nuclei they are not vibrators, but they are rotors. So we can imagine them having a shape like a rotating carrot. And actually this shape remains so constant as a function of the mass of the cadmium nuclei that the Z = 48 behave like if it's a magic number, but with a deformed nucleus instead of being spherical. In addition to that, what is very interesting from the study of mine, that not only I was able to study this deformation and shape evolving along the isotopic chain, but I could study even within, in details within one nucleus, that in this case was cadmium-106. And here we can see again that the vibrational-like structure that we have of this nucleus practically it seems to be due to the coexistence of different shape at the same time within the same nucleus that rapidly evolve as within the same nucleus. So practically we have that each different shape is related to a different proton configuration. In addition to that, so here I show some example of the interest of shape and structure. So the shape from the point of view of the nuclear structure, but shape is actually important also for other phenomena. For example, has a great impact in the study of neutrinoless double beta decay, which is a speculated and very extremely rare transition that laboratories and theoretical groups all over the world has been focusing on studying this kind of phenomenon. That the reason behind this is because the observation of such a phenomenon will tell us that there is more physics behind the standard model, and also the observation of such a decay would also tell us, give us information about the mass of neutrinos. But if we have a look at this formula here, where I'm not going to enter in the details of the different terms, but in this formula here, one that is most important, at least from my side, is the nuclear matrix element. That is one of the components that has the larger uncertainty right now, and where it has inside the information of the mother and daughter nuclei during this decay. And in particular, it has the information related to the deformation of this nuclei. And in particular, I've been working inside a collaboration to study the tellurium-130 and xenon-130 that are two candidates for this decay. And in particular, I'm taking care of the study of the deformation of tellurium-130. And here I marked, here we can see the picture of how much is supposed to be the nuclear matrix element for this decay. And in particular, here I marked in pink the shape that might be the tellurium-130 that I got from very preliminary results. Then last but not least, I spend a few seconds to comment also on another project of mine that I've been working recently, because not only to perform this kind of study, not only is important the gamma part, so very advanced gamma ray, gamma detector array, but also is combined particle and gamma spectroscopy. So even particle detector is very important. So recently I've been designing this new detector that is called Mosaic, that take advantage of the most advanced digital electronics and technologies on detector material in order to build a new detector and open a new field of research of Argonne National Laboratory and continue in order to continue my research on nuclear structure and nuclear shape. Here I conclude, summarizing what I said, and in particular I want to point out not only the importance of nuclear shape and the connection between nuclear shape with nuclear structure, but in particular I want to point out the fact that the study of nuclear shape has a huge impact in several phenomena of physics, not only related to nuclear structure. And here, for example, I just gave an example for the neutrino-less double beta decay. So thanks to all of you for all your attention, and also thanks to all my collaborators that has helped me during all these years. Unfortunately, if I put all their picture will take too many slides, so here I report just their institution. Thank you very much.
Okay, questions?
Yeah, I have a
Claudio, I'm going
question.
to ask, if you don't mind, a quick question, because I have to really leave at 10. So then I'll sign off. Mark, again, thanks. These are really three nice presentations. So very instructive and complete, but you know, even with a very small time. But one question I had is going back to the first question that actually Tommaso and I asked about machine learning. So nuclear physics is so complicated, you know, modeling nuclei is so hard. Is it conceivable to actually use some sort of machine learning where you just feed all the phenomenology that is known and try to see whether you can predict anything?
So nowadays there are many theoretical groups that are being working on using machine learning in order to, as you said, to describe the nuclear and to have to keep into account all the possible observables and so on. The problem here, and I've been followed many seminar and workshop in which these kind of things this topic was discussed. The main issue is the selection of the observables that you want to use to train your neural network, your machine learning. Because as for, let's say, with standard theoretical models, you select specific nuclei, specific observables in order to get the parameters of your interaction. Also here you have to say, you cannot put everything together, all the knowledge on the nuclei, let's say that we have, but you have to select. For example, I want to use excitation energy, I want to use the deformation, I want to use stable nuclei instead of radioactive ones. And what was, at least I've not updated to the very last version of these studies, but what was the problem? It was exactly this, that when you were selecting certain nuclei, these models were very good at reproducing, let's say, close by the neighboring nuclei, but as soon as you were trying to predict what was happening for a nucleus just farther away, so something more exotic, the prediction were completely that they were changing completely depending on which set of data you were used to train your machine. So that is something that has been exploring, and it's probably is going to be the future for nuclear physics. But at least nowadays, this is the limitation and the problems behind that, at least for the best of my knowledge.
Thank you.
Other questions?
Yeah, I have a question. So, and this is mostly my ignorance of the field. It's very far from what I do, so forgive me for my ignorance. So I'm curious about some of the sort of broader implications of this work. You highlighted one very nice that I like, the one with the double beta decay in the nucleus. Of course, that's a connection to fundamental physics. Are there any other connections to other areas of physics that you see for this kind of work? And can you highlight some of them for me?
Yes. So here I have a couple of backup slides just to give an idea. So for example, there is an effect, a very strong relationship between the nuclear structure and radiotherapy, in particular hadron therapy. In fact, because for example, nowadays the most used ions to do hadron therapy is practically used at ion, that is, let's say, can in this case I call projectile, in order to lose energy inside a tumor and burn and kill practically the tumor cells. In hadron therapy, one of the two most used ions that are, for example, proton on one side. If I remember, in Catania and in Poland, there are these huge facilities where they do this treatment of the eye tumor with protons. But also another one is carbon, that since is heavier, it loses much more energy inside the tissue and burn, let's say, easily the tumor cell. On the other hand, one of the things that happen when you use a carbon beam, you have what doctors have observed is that, okay, I burned very easily my tumor cells, but at the same time, what they observe is that the neighboring cells were damaged. So, and in most cases, that the tumor was then, another tumor was rising far away from the original spot. And that's actually, let's say, this is actually understandable if we look from the shape and nuclear structure point of view of carbon. Carbon has a structure that is like having 3 alpha, so 3 helium-4 structure inside itself. So what is happening is that you can have that because of this alpha cluster, you can have collateral damage due to the fact that this carbon breaks, and then you have this spare alpha particle that is going not anymore straight to where you're shooting, but is going far away. Another relationship, for example, between nuclear structure or, again, nuclear shape and physics is, for example, the stellar burst. So for the moment, we always study the behavior of a fusion reaction inside stars, like having 2 nuclei that they close by together and they do and they fuse together. However, this change a little bit when we have to deal with the deformed nucleus. Because while in order to fuse, the 2 nuclei have to pass through the Coulomb barrier, but this is set by the atomic number of the 2 partners. This hill, for example, here I put the potential, the potential for the nuclear potential. Practically, the fact that we are dealing with a deformed nucleus, it changed the range of this hill on the left. So depending if you are hitting your nucleus depending from the thinner part or from the larger part of your deformed target, let's call it target, it changes how large or shrink is this hill. So it changed the probability for having this stellar burst. These are just, for example, two examples that I reported in order to show that the study of nuclear shape is not interested only for the, let's say, the sake of nuclear structure point of view.
Thank you, Marco. Much appreciated. I'm sorry to everyone. I'll have to disconnect. Wonderful presentations, everyone.
Thank you for being with us, Tommaso. All right, other questions? If not, I would like to thank the three finalists for their very interesting and beautiful presentation. And I want to thank also the jury for being here and having now a difficult task to go from 3 to 1. And I want to thank the ISSNAF administrators, Enrica and Cinzia, for organizing this Zoom today. And with this, should we add something else? Enrica, Cinzia, would you like to add something?
It has been a pleasure for me to listen to this presentation. Of course, I'm not in the field, but at a very high level, at least a very, very high level, I was able to have a sense for what everybody's working on, and speaking for the general public, I'm very pleased. So thank you. Good luck to our young scientists, and thank you to the jury. And Claudio, thank you very much to you for hosting today. So with this, we'll close the webinar.
Okay. Bye, everybody. Arrivederci.